Hi everyone, let's do a roulette example where we have to come up with the distribution table, unlike in example 1 where it gave the table to you. Let's figure this out. So let's say that in order to play a round of roulette at a particular casino, you first pay $100. If you bet on red and a red number comes up, that is if you win, then you win $200. If you bet on red and another color comes up, then you win nothing. Let X, I'll put this in green, let X be your net monetary gain as a result of playing a round in which you bet on red. Find E of X, the expected value, and interpret it. We're assuming that the roulette wheel is typical for America: 18 red slots, 18 black slots, 2 green slots, for 38 slots total. Here are the corresponding probabilities for red, black, and green. So we'd like to fill out a table like this. We want to figure out the distribution table for X. So basically, you either win or lose. And I'd like you to figure out the value of X. What is your net gain if you win versus if you lose? And what is the probability that you win versus if you lose? I'll put the reminders up here. And I'll give you a minute to figure it out. Fill out the table. All right. So if you win, if the roulette wheel comes up red, your favorite color, you're betting on red. If you win, what happens? Well, you win $200, but wait a minute. Remember, you paid out $100 to play the game to start with. So your net gain, the value for X in this case, would be $100. If you lose, what happens if you lose? If you lose, then you win nothing, but you're still out the $100. So your net gain is negative $100, meaning they have a net loss of $100. If your net gain is negative, that means that you've suffered a loss. So that's the X column here. That's the X column here. If you win, your net gain is $100. If you lose, your net loss is $100, meaning that your net gain is negative $100, the value for X. And what are the corresponding probabilities? Well, you win if the roulette wheel comes up red. The probability of that happening is this over here, 9/19, or about 47.4%. Now, what's the probability that you lose? The probability that you lose is going to be 9/19 plus 1/19, because you lose if the roulette wheel comes up black or green. So you lose with probability 10/19. or about 52.6%. So here is the full table in its full glory. If you win a net gain of $100 with probability 9/19. If you lose, your net gain is negative $100. That is, you have a net loss of $100 with probability 10/19. Here's the table cleaned up. To find the expected value of x, it's the zigzag. It's this times this plus this times this. The zigzag. So E of x, or mu, is 9/19 times $100 plus 10/19 times negative $100. That's negative $5.26. The interpretation: if you play many rounds of roulette, think 1,000 rounds. I hope you're not that much of a gambling addict, but if you play 1,000 rounds of roulette at this casino and you always bet on red, you love red, your long run average net loss will be about $5.26 per round. Now, it's good to interpret what a negative sign means. So you either want to say that your long run average net gain is negative $5.26, but since we don't like to use negative signs in our interpretations, we like to interpret what the negative sign is. So you should say that your long run average net loss will be about positive $5.26 per round. But it's either one or the other. Your net gain is negative or your net loss is positive. It's one or the other. Don't do both. Don't say your net loss is negative. That's a double negative. All right. Interpret negative expected values appropriately. Now, the reason why, if you play many, many rounds of roulette, you get this as your long run net average is because of the law of large numbers, which say that the probabilities that are built into the game will crystallize in the long run. So in other words, the observed relative frequencies of red, black, and green will approach the corresponding theoretical probabilities, the probabilities that we had listed way up here. In the long run, the observed relative frequencies of red, black, and green will approach these theoretical probabilities, 9/19, 9/19, and 1/19. Okay. And because of that, we expect this long run expected value to represent your long run expected average in the long run as the number of rounds approaches infinity. Now, because the probabilities will crystallize in the long run, and because this payoff structure actually works against you, because remember, a fair payoff would allow you to win a bit more than $100 if the expected value is truly to be $0. For a fair game, by definition, for a fair game, that is a fair payoff, the expected value of x should be $0. That means no harm, no foul. That means that in the long run, you don't expect either the casino or the player to make a gain. But of course, casinos are in it to make money. So if E of x is the expected value of x, where x is the net gain to the player, right, then E of x will typically be negative if you're playing a casino game. In order for E of x to be 0, this would have to be a bit more than $100. Think about it. If you had to make a lot of money, how do you maximize your chances of winning a huge amount of money? My suggestion would be put it all in one shot and hope. Because in the long run, the law of large numbers will kick you because the payoff structure is set up so that E of x is negative. If E of x is negative, this is not a game you should be playing in the long run. You should not be playing casino games in the long run. You should not be a gambling addict because the payoff structure forces E of x to be negative, where x is the player's gain. So in the long run, casino games hurt you financially. That's the key lesson here.